This is Applied Calculus, Section 1.6, Logarithmic Functions. We start by identifying a new type of function called a logarithm, and it is the inverse of its exponential counterpart. And our textbook just wants us to get familiar with the location of the log keys on our calculator. You'll notice that the TI calculator places the log key with its inverse function as the secondary key. Notice that the blue 10 to the x, you'd have to hit the blue second button up at the top to access it. But this just lets us know that on a calculator, when we see log, that is the same as log with a base 10, and this is the inverse to 10 to the x. We also have an ln button here, and above that e to the x. So whenever we see an ln button, it is the same as log with base e, and ln is the inverse to e to the x. As we move forward, we have some definitions we want to go over. What does it mean to be a one-to-one function? Well, when we first defined functions, we said that only the domain values can be used exactly once. Now we're saying if the domain values are used exactly once, we have a function, but if that function uses its y values exactly once, then you have a one-to-one function. Our next definition, inverse of a function, states that if f is a one-to-one function, then the inverse of f is the function formed by interchanging the independent and dependent variables. That means switching your x and y values of all your points. Therefore, if AB is a point of the graph of f, then BA is a point of the graph for the inverse of f. Final note, if f is not one-to-one, then f does not have an inverse function. So we're going to derive where the logarithmic function comes from, and we start by taking y equals 2 to the x, our exponential. And if we plot a bunch of points, you see that we get this graph up here. All of the points, we plot them, we go, great, this is the exponential function 2 to the x. But if we were to take some of these points, so right here, this is the point 1, 2. If you take the point 1, 2, and you switch the x and the y, you get 2, 1, and we see it plots on the other side. If I take 2 and plug it into the exponential, I get 4 as the y, but if I switch those values, 4, 2, 1, 2, 3, 4, 2 up, we get this point. So we take each of these points and we plot them, and when we graph them, we get this inverse graph. And you should see that this inverse graph is a mirror image of the exponential graph. And this line is y equals x, the identity function that creates the mirror through the origin. And each of these points is a reflection. So we were able to plot the inverse function's graph. And we said, well, basically what we've done is we've taken y equals 2 to the x, and we switched the values x equals 2 to the y. We switched x and y values. And if you can do this, you can then write a new function which says that the y coordinate is equal to logarithm with a base 2 and an argument of x. And this is true if and only if you can plot the inverse function's graph by exchanging the points. So let's look at our definition a little more closely. The inverse of an exponential function is called a logarithmic function for b greater than 0 and b not equal to 1. So we have the same properties as an exponential function because the logarithms are an inverse to that. So this is the logarithmic form of our equation. Notice the base value is beneath the log, and this is equivalent to x equals b to the y. Well, if we're solving for y from a log function, we must identify y as an exponent. And if we think of y as an exponent, it will help us in understanding the properties of logs and evaluating them without calculators. So example 1 says change each logarithmic form to its equivalent exponential form. Remember, this is the y, because we have y equals log base b of x. And we want to write this as x equals b raised to the y power. Well, x is 25, the base is 5, and y is 2. And we say, well, 5 raised to the second power is 25. 25 is equal to 25. And we say, yes, all of this balances out. This is our base. This is our exponent. So we want 9 to the half power, and that must equal our argument 3. The half power means square root. And we see everything balances out. Part C, this is our base. We have a base of 2. Y is our exponent, and our argument is our answer here. A negative exponent means reciprocal, and we see this balances out. And we do all of this so that we can then start to solve logarithms with some unknown arguments. So we're continuing with the rewrite practice. How do I find the logarithmic equivalent of this exponential? Well, we're going to reverse everything we just did here. Instead of taking the log and putting it as an exponent, we're going to take the exponent and put it as a log. So we know that the base is 4, so log base 4. The argument is going to be 64, and the exponent is going to be our y. So we have that y equals log base b of x format, and that's the logarithmic form of that exponential equation. So let's do the same thing for part B. 6 equals square root of 36. I need to write that using exponents. Now I know my base is 36. My y is my exponent, so 1/2 equals log base 36, and then my argument is 6. So you have to remember, 36 raised to the 1/2 power equals 6. That all balances out. And this is going to help us solve logs by recognizing these patterns that exist in writing the exponential versus logarithmic form. Okay, part C, the base is 2. The exponent is -3, so that's our y, and our argument will be 1/8. 2 raised to the -3 power is the same as 1 over 2 raised to the 3rd power, which is 1/8, and that matches the argument. So now we can find solutions without a calculator. So it says find y, b, or x as indicated. Part A says find y. So y equals log base 4 of 16. And this is where I said you have to keep recalling y is an exponent. So if I take the base, which is 4, and raise it to the y power and say this has to equal 16, the whole purpose of this is you've now created a question for yourself. 4 raised to what power is 16? Hopefully you say 2, so y is equal to 2, and that means you can answer this logarithm now. Y equals log base 4 of 16 means that y is equal to 2. Part B says solve for x. So we have log base 2 of x equals -3. Remember, this is our y, so this is our exponent. This is our base. So we can say 2 raised to the negative 3 power equals x. Remember, negative means reciprocal. So 1 over 2 cubed equals x. X is 1/8. And part C says find the base. So we have log base b of 100 equals 2. And we want to write the base b raised to the second power equals 100. We should be able to ask ourselves, what number squared equals 100? And hopefully you say 10. 10 times 10 is 100. So b equals 10 is the answer. So we can solve these logarithmic expressions and find the unknowns by using the relationship or the inverse relationship between logarithms and exponents. Theorem 1 discusses some of the properties of logarithmic functions. It says if b, m, and n are positive real numbers such that b is not equal to 1 and p and x are real numbers, then the following properties apply. Log base b of 1 is 0. And remember, the 0 is the exponent, the b is the base. Any base raised to the 0 power is always 1. So any logarithm with an argument of 1 will always be equal to 0. Property number 2. Remember, b is the base and the y is the exponent, so b raised to the first power is itself. Anything raised to the first power is itself. Property 3. Log base b with an argument of b to the x is equal to x. So what we have here is a log function and an exponential function, which we said were inverses. And a property of inverses is that when you compose them together, they extract the argument, they extract the variable. So let's show you another example. If I had f of x equals x cubed and g of x equals the cubed root of x, if I put one function inside of the other, so this is f of x composed with g of x, and this can also be written as f of g of x. So it's two different notations that mean the same thing. It says when you put one function inside of the other, if they are inverse functions, they will extract the variable. Well, let's look at what it's like to take g of x and plug it in for the x of f of x. We would get the cube root of x inside of the cubing function. And when you cube the cube root, you would get just the x. And if you did it in the reverse order, if you did g of x with f of x plugged inside, you would have the cubed root on the outside and the x cubed inside, and the cube root would cancel out the cube and give us just x. And we can work out many other examples of other functions that have inverses, and it'll show that anytime you compose the two together, you get just x. And property number 4 is the same as 3, but in the reverse order. So exponential functions and logarithmic functions are inverses. These two will cancel each other out and leave behind just the x. So just as I did the f with the g of x inside, or the g with the f of x inside, and we saw that it always came out to x, they just switched. Are you plugging the exponential inside the log or the log inside the exponential? But because they are inverses with the same base, they will extract the argument, and that's a very important tool for solving. It's how we get the variable out of a log or get the variable out of an exponential function. As we continue looking at the properties, if we have the log of a product, we can split that into two separate logs. If I take log base 2 and do 5 times 6 and hit enter, I get 4.90689. But if I did log base 2 of 5, and then I added log base 2 of 6, you see we get the same answer. And this is because logs are exponents. And what do you do when you have two expressions multiplied together with the same base? You add their exponents. And that's the link between the log property and the exponential property. And what did we do with exponents when we divided them? Well, we subtract those exponents. Remember the theme, logs are exponents, so now we're subtracting them for rule number 6. And you can take a numeric example, plug it into your calculator like I just did for number 5, and see that you get the same answer if you use the left-hand format or the right-hand format. 7 gives us the power property for logs. So if I have log base b of an argument with an exponent, I can rewrite it as that exponent times log base b of m. And finally, log base b of m is equal to log base b of n if and only if m is equal to n. Just like we had that property with exponentials, that either the two bases must be equal given equal exponents, or the two exponents must be equal given equal bases. So example 4, we're going to use some log properties to rewrite this. So we see that we have a fraction here, so we can write this as log base b of wx and subtract log base b of yz. But now we have a multiplication here, so we can break it down further, say log base b of w plus log base b of x minus, now I'm going to put parentheses because these two expressions need to both be affected by the minus, log base b of y plus log base b of z. And when you distribute that minus through here, you can simplify this to be log base b of w plus log base b of x minus log base b of y minus log base b of z. And that would be completely unpacked. If we do this for part B, I'm going to use the power property first to rewrite this as 3/5 log base b of wx, and then this becomes 3/5 log base b of w plus log base b of x. And then if you wanted to go one more step, you can distribute this 3/5 in front of each of those. Part C, we have e to the x log base e of b. And I can write this as e to the log base e of b to the x. These two will cancel out and give me b to the x. So example D requires a little bit of clever algebra. We see that we have a log with a base e and an argument of x in the numerator, and a log with a base e and an argument of b in the denominator. Because we have two logs with the same base, we feel like we should be able to do something with them. So this is somewhat of a clever move using the algebra and the properties of logs. Understand that x is the argument and b is the argument in the denominator. So by adding those parentheses, I can now say b raised to the log base b of x and hopefully you're saying, well, where the heck did you get that from? What makes you be able to do that? Remember that the inverse property allows us to say these cancel and we extract the argument and the x would come back out and look just like when we started. Conversely, I could have had something like this where the inverse property applies, the x comes out. So depends which situation you're in that it would apply. So continuing with that, we can now say that log base b of x to the n, this is one of the log properties, I can rewrite it by taking this and putting it out front, n times log base b of x. And we say, all right, in this pattern, the e is the base of my log, the x is the b, and this exponent that's going to come out in front is log base b of x. This we're going to be allowed to pull out front. This is the power property for logs. So let's erase this, continue with our sophisticated algebra. So that exponent comes out in front. We have log base b of x times, and here we have log base e of b. All over the denominator, log base e of b. So we've used these log properties to rewrite it, and much to our surprise, log base e of b will cancel now, and this gives us a final, simplest form of log base b of x. So I wanted to get the x paired up outside of this so that I can get a log base e of b inside of here. And that's why we said, well, let's take b raised to the log base b power with x as the argument, because these are inverses and would cancel. That give us back our original function if we wanted it, but we didn't want that. We wanted to pull it all out front here, so we had matching terms that would cancel. And that's our final answer for simplifying example D. So here, for example 5, we're going to solve an equation. And from this equation, we have a bunch of different properties that we're going to implement. So I notice that all of my logs have the same base. So to start with, I'm going to reverse the property. I'm going to take what's out in front here and put it up into the exponent. Say I can write this as log base b of 4 to the 3/2 power minus, I'm going to take this and put it out in front of the exponent, log base b of 8 to the 2/3 power, and then plus log base b of 2 equals log base b of x. Now that I have these all with the same base, we can start to apply the log properties that when I subtract them, I can express them as a fraction. So when I subtract these logs with the same base, I can express them as a fraction. 4 to the 3/2 over 8 to the 2/3. And now the plus says I can multiply. So log base b of 4 to the 3 halves times 2 over 8 to the 2 thirds equals log base b of x. And now that I've got these expressed as log base b's with arguments, the two arguments must be equal. 4 to the 3 halves times 2 over 8 to the 2 thirds must equal x, and we can simplify this. 4 to the 3 halves is going to be 8. 8 times 2 will be 16. 8 to the 2 thirds will be 4. 16 over 4 gives us 4. So x is equal to 4. So here we have another example. It's already set up with all of the like bases. So we can say that I can combine the left-hand side because of addition. I will multiply the arguments. So log base 10 of x times x plus 1 equals log base 10 of 6. And now that we have these as a single log on both sides, we would just take the arguments and set them equal. And if I distribute here, I have x squared plus x equals 6. Since this is a quadratic, we need to get 0 on one side. It's a quadratic with a lead coefficient of 1, so we can just write out the factors. Two numbers that multiply to negative 6, but add up to positive 1, plus 3 and minus 2. So we have x is equal to negative 3, and x is equal to positive 2. Okay, so here's example 7. Just using calculators and rounding to 6 decimal places. We'll get our calculator. This is log, so we use the log base 10 button. 3184. Hit enter. And it says round to 6 decimal places. So that's our answer for A. For B, we'll hit the LN button. So we have a negative 7.960438. And for C, the log button again, negative 3.24. We see that an error comes up. So y equals log base 10 of negative 3.24 means that we should be able to write 10 raised to the y exponent equals negative 3.24. And this is where the problem is. How can you multiply 10 by itself so that you get a negative answer? And you can't do that. So you can't change signs with exponents. You would need to add or subtract something from it. So if I had 10 to the y minus some number a, I can get negative 3.24. But simply through exponential or logarithmic actions, we cannot. So this is not in the domain. So now we'll use our log properties and the calculator combined to solve for these values for the log. It says find x to 4 decimal places. So we understand that whenever log does not have a base showing, it is log base 10. And we're saying that y is the exponent, so 10 raised to the negative 2.315 is equal to x. 10 raised to the negative 2.315 gives us x is 0.0048. Now you can also use your calculator's log feature to do this. You can type in log of 0.0048 and see if we get back negative 2.315. Negative 2.318, that's because I rounded. If I hit log and I go back and get the full answer without the rounding, I see I get negative 2.3149999. So that is the 315 that we were looking for. So part B is using ln. ln is understood to be log base e of x equals 2.386. And the exponential equivalent second e raised to 2.386 gives us an answer of 10.8699. Again, if we want to test this, I can take the natural log of our answer. We get 2.386, so that matches our answer we have if you round it to the third decimal place. So that's good. So now we're going on to solve exponential equations. And it might help us this time to rewrite this as a logarithm. So remember, logs are the exponents, and they're going to have the same base. So we're going to say x equals log base 10 of 2. And if I plug this into my calculator, we get 0.3010. So if we raise 10 to this power, will it give us 2 or something very close to 2? And we see we get 1.99986, so we're satisfied with that answer. Okay, so e is the base, so we should use natural log because it has base e. And then the argument is 3, and the exponent is x. Natural log of 3 gives us 1.0986. And if we plug this into the exponential, it should give us an answer very close to 3. And we have 2.9 repeated. So it's always good to go back and do the double check, because you never know when even though you've typed something to a calculator, gotten an answer, go back to the original equation and make sure that everything is near the original state. It'll be slightly off because we're doing some rounding. So now we're looking at something with a different base. So we need log base 3 of 4 is equal to x. Now, if we have the Texas Instrument calculator, you can write logs of different bases by hitting the alpha button and then the window button, and you see log base is option 5, so I'm going to hit 5. And now I can put a 3 in for the base and a 4 in for the argument, and it tells me 1.2619 if we round to the fourth place. But what if you don't have the Texas Instrument calculator? Then you need to use something called a change of base formula, which says use either the log button or the ln button on your calculator. Doesn't matter which one. So if I use log, I have to use log for both the numerator and the denominator. So log 4 over log 3. Notice that we took the argument and put it in the numerator log, and we took the base and we put it in the denominator log. This is called change of base because we're changing from base 3 to base 10. And whatever the answer is you get here, it would be the same answer if you used the natural log of 4 divided by the natural log of 3. Change of base says you can change it to any base and get the right answer. So let's look at this in our calculator. We put in log base 3 of 4 and got this answer. But now if I do log 4 divided by log 3, because maybe my calculator doesn't have that fancy way to put logs of all bases in, I need to use this technique, and I get the same answer. And if I press the ln button instead, we get the same answer. So using the correct base, or the change of base with base 10, or the change of base with base e, we see the answer is the same all the way through. So that lets us evaluate logs of different bases on calculators without this feature. So example 10 is an investment problem. How long to the next whole year will it take money to double if it is invested at 20% compounded annually? So since it's compounded annually, that means it's compounding once per cycle. So we can say we want to double our investment. So that means that I want my output for A to be twice as much as my input for P. So let's just make these the simplest numbers. Invest $1, get out 2. 1 plus 0.2 over 1 simply reduces to 1.2, and 1t becomes a t up here. Now anything times 1 is itself, so I can say 2 is equal to 1.2 to the t, and now we will solve for t to find out how long it takes money compounded annually to double with a 20% rate of return. So how do I get this exponent out? Well, the inverse of exponents is logarithms. So if I take log with a base 1.2 and apply it to this side, then they will cancel each other out because they're inverses, and that will take out my t. But anything I do to one side of an equation, I must do the same exact thing to the other side of the equation. That is a basic law of algebra. And now this is the equation I want to solve. I took compound interest formula, plugged in the known data, simplified it, and then noticed that my variable was in the exponent. So I needed to extract the variable from the exponent. Logarithms are inverses to exponents and will let me extract a variable. So this is my logarithmic equation to solve this. Now we know that this side will simply cancel out and give me that t is equal to log of base 1.2 with an argument of 2. If you don't have a calculator that can enter this, you can use the change of base calculator formula, log 2 divided by log of 1.2, and that'll give you your answer for t. So I'll do this with the correct base of 1.2, and I get 3.8 years, so 4 years. They want us to go to the next whole year. But if we use the change of base formula, log 2 divided by log 1.2, we get the same answer, or you could have used ln, but about 4 years is the answer. And we'll finish with a regression problem. The U.S. Census Bureau published the data in Table 1 on home ownership rates. Let X represent time in years with x equal to 0 representing the year 1900. We're going to use a logarithmic regression to find the best model to fit the form y equals a plus b times log of x. So that form for home ownership rate y as a function of time x, we're going to use this model to predict the home ownership rate in the year 2025. So regression models, you can either use your TI calculator or you can go to section 1.4 and use GeoGebra. And I showed you how to do regression analysis in GeoGebra in that lesson. I'm going to open up the calculator. I'm going to go to my stat, edit. I see there's data in my lists. I'm going to go stat. Number 4 is clear lists. I'm going to hit the second and then the 1 key to choose list 1, then a comma, second, the 2 key to choose list 2. When I hit enter, those lists are clear. I can go back to stat, edit. I'm going to move back to L1 because that's my x values. Up above it said 1900 is x equal to 0. So that means that 1950 will have an x of 50, 60, 70. So these are the x values we're going to plug into the calculator. 100, 110. Hit the right arrow. We can put in our y values. Now we hit the stat. Up on the top, we want the calc menu, so we'll hit the right arrow. And we're going to go down the list until we see, notice that in the formula, they have ln here. ln of x is what we're looking for in our calculator regression. So we're coming down the list. That's line. There's ln reg. So that's the logarithmic regression model. We'll hit enter to choose option 9. My x's come from list 1. My y's come from list 2. Then I go down and choose calculate and hit enter. And here are my values. So 4.113 is my A and 13.596 is my B. So we can use this now to write y equals 4.113 plus 13.596 times ln of x. Now to find home ownership in the year 2025. 2025 minus the year 1900, because 1900 is our 0 year for x. That gives me 125, and that's what we want to plug into x. And it looks like 69.8% is the home ownership rate for the year 2025. It seems to fit in line with the data trend. As home ownership rates keep increasing, we're on that path still. So that is the end of this lesson. Rewatch the video, take your notes, complete the practice assignments, and come to class with questions.